All right, let's continue. Any questions? Any comments? So I want to start talking about Josephson junctions and show you how these devices actually manifest this Cooper pair condensates we've been talking about. So the system is something like this. Suppose I have like a superconductor, something like this. I have like some superconductor, some wave function with some phase. And what I want to do is I want to bring this superconductor in contact with like a second one. Something like this. I don't know, this is psi 1, E1. It has, the order parameter has both a norm and a phase. And there's like a second one here, a norm and a phase, and in between there is like a thin insulating layer. So this is the distance between these two surfaces, something like L, and we are assuming L to be much smaller than Ginzburg-Landau coherence length, or Cooper pair dimension. Good. And this was first considered by Josephson. I think it was his like PhD thesis, and I think he did like this like amazing work. He got the Nobel Prize, and then he started doing like I don't know spiritual and some I don't know what, but hopefully you will see this is actually very important and very like groundbreaking. So the idea is there's like some quantum state here, quantum state there, and because of quantum tunneling, right, the electron here can just go from here to there, right? Let me call this left side and right side, and consider tunneling. L and R, and using our fermionic fields we introduce, we can write the tunneling Hamiltonian. So H tunneling is equal to some tunneling amplitude, which doesn't concern us. It's like specific value, like psi something like left dagger, and psi right. This means take something from right and put it to the left. Or I also have to have the opposite amplitude. Take something from left and put it right. Psi right dagger, psi left. So we'll see later in the BCS theory that if you calculate in the first order perturbation theory, right, there is like some psi on this state and psi on this state, and you can calculate the expectation value of this tunneling. You are going to find 0 because there are like, if you want like n electrons here and let's say n electrons here, after this one there is like n minus 1 here and n plus 1 here, and before and after states are not the same, so expectation value is going to be 0. So no single particle tunneling. So this can actually happen when you have the leads and you have like a grand canonical ensemble. This can also happen, but even then it is forbidden because also because of BCS gap. Let me just not mention that too much because we are going to be talking about this a lot. For the moment it's not very important. What is important is like to lowest order there is no tunneling. And we need to consider the second order, something like ht squared can contribute. And the form is what? We need to take the square of this, and ht squared is some, right? We are not doing like a full calculation. We are trying to understand what comes out of this thing, and it is something like this, right? Some t squared times psi left dagger, psi left dagger, psi right, psi right. There are other matrix elements, but I am only writing the important one for us. Plus the opposite, psi right dagger, psi right, psi, this is dagger, psi left, psi left. And you can see this corresponds to taking a pair from the right superconductor and putting it to the left, or taking a pair from left superconductor and putting it to the right. So these are pair tunnelings. At least that's how Josephson came up with his effect. He considered these tunneling matrix elements and he calculated these things carefully. But we don't have to do that, right? What we care is the average value of this thing, the expectation value of this, and assuming right and left superconductors independently have their coherent state, or like a Cooper pair wave function. What we need to do is like take this thing and do the expectation value like this times this thing. So this is proportional to plus exactly the same thing here. This thing times this thing. So this is exactly the order parameter, or off diagonal long range order we introduced in the first hour. So if, for example, here I have some Landau wave function, let me write it psi right, e to the I right, and this is going to be this Landau wave function psi left, if you want it is the norm, psi left, e to the minus I theta left, and the opposite on the other side, the second term. So this is psi right, e to the minus I theta right, and psi left, e to the I theta left.
Is this the reason why you don't take this gap very intensively?
Yes, because like it is not it is actually from the tunneling, right? If you have like quantum mechanical tunneling, right, as the width of the barrier increase, you decrease the tunneling amplitude exponentially, right? So there's like some e to the minus, I don't know, k, l, something like that. Because of this length, the wider the barrier, the smaller the chance of tunneling.
We separated this expectation values like because of this barrier.
I think it is not because of the barrier. I just assumed there's like a separate superconducting states on the left side and the right side. But the point is, these independent condensates are connected with tunneling matrix elements. And to second order in perturbation theory, the tunneling matrix elements gave us order parameters of each lead. And this gave us a correction in the energy, right? Because this is expectation value. So what I want to assume here is like, suppose I have the same superconducting state, right? I take one superconducting state and I cut it like a knife, right? I separate it in two. And I'll show you pictures that this is actually, people do these things. And I'm going to only have like the same order parameter here and there, but the only difference could be the phase difference. Like I have exactly the same superconducting state, but since the phase is arbitrary, there could be a phase difference between left and right. Therefore, this thing is going to be of some, I don't know, psi 0 squared e to the I theta right minus theta left, plus again psi 0 squared e to the minus I theta right minus theta left. And from here we see, like, let me call it E, so this is the contribution to energy from the junction, is some constant, which is typically called Josephson energy, right? And this is cosine theta right minus theta left. Or let me just write it like cosine delta theta, where delta theta is theta right minus theta left. Good. So if I give you the energy, right, I can also consider the current. Like current is exactly the same thing, like Cooper pairs going to the left minus Cooper pairs going to the right. And the only difference is going to be this plus is going to be minus. Is that clear? Right? Because I'm looking at the current going to the right is what? Or current going to the left is what? Take from right and put it to the left. And current going to the other way is like take from left and put it to the right. Then the difference is going to be like a minus here. Therefore, I can also calculate J is going to be, or let me call it I, some I constant times sine delta theta. By the way, we can also calculate this I from the derivative of this del E del theta, right? Can also be used. So this thing is what we call DC Josephson effect.
Is IC complex then?
So no, it is just some constant, right? Because we are taking the expectation values, right? And this is an expectation value of an Hermitian operator. It is real, right? This is operator minus its Hermitian conjugate. If it's not real, you need to make it real.
Because this, e to the power formulation just good.
Oh, yes. I think you need to take care of I.
When it is minus, you need to put an I?
Yes, and then you need to find a way to cancel that I. But this one doesn't have that problem, right? This one, if you take energy and take derivative of energy with respect to phase, it's also current. You can compare this, but we said J was del H, del A, right? And A is connected to phase. Yeah, anyways, this is real. So this is direct current, Josephson effect. Actually, let me give this part as an exercise. If you have the appetite, you can do this. So exercise. Consider SIS junction. So this is something like that. I have drawn a board, something like this, and another one here. And there's like some distance here, L. So this is SS. And reduce Ginsburg-Landau equations to this form. I think we already did it in the class, but you can do it again. D squared F dx squared plus F minus F cubed is equal to 0. And in the limit L much less than psi, drop F and F cube. So you can drop these two terms in that limit, and that's like simple Laplacian in one dimension, right? And the boundary conditions, psi left is some psi 0 times e to the I theta 1, psi right is some psi 0 times e to the I theta 2, and find psi, the solution, and from there put it in the current. Right, we also had like a current expression for Ginsburg-Landau, and also find j. And from there you are going to find this sine theta either way. So this is like, right, this is not very easy to accept. What this is saying is like, even if you are not driving any voltage, right, current comes with voltage, right? You apply a voltage difference, right? You put the voltmeter leads and they drive the current and electrons flow. But here you are saying that even without that, there is like a current. And this current is super current, like so this is superflow. And that's why people did not want to accept it when Josephson first came up with this idea. And the second step is like, suppose there is like this supercurrent and I want to also apply a voltage difference. And let's see what happens. And this is going to give us AC Josephson effect. AC Josephson. So let me try to cut the unimportant terms in the Hamiltonian and just write the terms that gives this effect. So I can have like I h bar del psi left del t. So this is the change in Ginzburg-Landau order parameter with time, and it is going to have some E1 psi left and I h bar del psi right del t is equal to some, let me write this EL. So this is E right, psi right. And let's write psi left as psi 0 times e to the I theta left, and psi right as psi 0 times e to the I theta right. And this is constant. The only time dependent thing is going to be the phase. And this thing is going to give me psi 0 minus h bar theta left dot is equal to E left psi 0 e to the I theta left, and similarly minus h bar psi 0 theta right dot is equal to E right psi 0 e to the I theta right. And there will be real and imaginary parts, right? Real and imaginary parts. And theta is real, so the real part of this piece is going to be the real part of this. And imaginary part, which is 0 here, is going to be 0. At least in this.
Exponential part at the left-hand side. When we take derivatives.
But this derivative here?
Exponential.
Oh yes, these are cancelling, right? So this one cancels. Good job, thank you. Yes, so this is correct. Then there is no real and imaginary parts. Yeah, I think I was trying to cut these pieces from the exam. Then that's even better. Here I find so d dt delta theta is equal to E right minus E left divided by h bar time. That's it, right? Nothing else. And if I apply the potential difference like this, so suppose I apply like a potential difference here, V left, and this is V right. The energy difference is going to be just the potential difference times the charge, and this is going to be 2E times V right minus V left divided by h bar. So let V be defined by VR minus V left.
There should be another minus.
Yes, there is a minus here, but at the end what we have is like something like this. Delta theta of t is something like some delta theta 0 plus or minus, doesn't matter, 2e over h bar times v. And we put this in the Josephson current, so I is going to be this I critical times sine delta theta 0 plus 2, okay, there's t because I'm integrating, obviously, I'm integrating delta theta, needs to be t here, 2e over h bar v times t. So this one is AC Josephson current. And let's plot this and let's try to so this is current versus potential difference. And even when there is no potential difference, there is like a current here and here. If you want, there is like a current here, super current, like this. And as you increase V, right, sine is going to increase like this, something like that. Let me try to write. So at very large potential differences, this should converge to Coulomb, Ohm's law. Therefore, so this is something like this. So this is maybe, why is it like doing that? Okay, something like that. And from here, something like that. Okay. So this large piece is like normal state, Ohm's law at large V. And this is what people generally see in the experiments. Right? They tune voltage difference and they start with current even with zero. Okay, this is V. And as they increase, they go from DC to AC Josephson effect. Good. Any questions? So let's make it a little bit more interesting. Let's think about superconducting quantum interference. It's kind of like a double slit experiment, but done for like macroscopic waves and also with superconductors. So let's think about this. And the device for this effect is called squid, which has like a playful name, squid devices. And it is something like this. I want to have Josephson junction, but like in like a weird geometry. Let me draw it. Okay, something like this, and something like that. And what I want to do is I want to put a junction here and a junction here, and I want to flow the current from here to there. Okay, so this is I, and there you can see there's like a hole here. So there's like a hole, and in that hole I can, for example, pierce through a flux, a magnetic flux, and that's what I'm going to do later. First, let's think about this without the flux. I have like one phase difference here, like this is theta 1 left, theta 1 right, and this is theta 2 left, theta 2 right, this and this, here and there. They are like local phases. And the current, because this is like a parallel circuit, total current is this current plus this current. I is going to be, and I'm going to assume like a balanced upper branch with lower branch. It's going to be some I C sine theta 1 right minus, actually let me write it like this, delta theta 1 plus I critical sine delta theta 2. Phase difference in the upper branch and phase difference in the lower branch. Good. So this is without flux. Now I want to put here, right in the center of this loop, a magnetic flux. So this is solenoid with B flux phi. And now what happens? Let's think about the flux. Flux by definition is like this, D area times B, right? And the same trick we use all the time. We use the Stokes theorem. So this is some loop dr dot A. And for the loop, I want to choose a loop like this, something like that. And we know this thing can be related to the gradient of the phase, right? We talk about this like in Ginzburg-Landau, right? We have to have like gauge invariance, and vector potential and phase are connected. And a change in vector potential can be observed a change in phase, or change in phase can be observed a vector potential change, right? We had those. Therefore, this thing can be written as 2e over h bar, and this is the charge q of Cooper pairs times the r gradient of phase. I think we talked about this. And what happens here is like, let's go through this loop. I go through here, I pick up like this delta theta in the lower branch. So this is 2e over h bar. Delta theta, let me go through upper branch, it doesn't really matter. So I go clockwise and I pick up delta theta 1 in the upper branch, and I come back and I traverse the lower branch in the opposite direction, right? I go like this in the upper branch, go like this in the lower branch. That's why that's going to be delta theta 2 in the lower branch. And this 2e over h bar, I want to introduce this flux quantum. Flux quantum is, at least superconducting flux quantum is 2e over h. Then I want to write this as 2 pi phi naught delta theta 1 minus delta theta 2. And now I can choose like a symmetric, I can distribute the current symmetrically, right? In the presence of this flux, I can say, so half of this is going to come from like this, this is delta theta plus pi phi over phi naught comes from the upper branch, and delta theta minus pi phi over phi naught comes from the lower branch. I can say that for some delta theta. Then if I write the current corresponding to this, I'm going to have I is equal to I critical times sine delta theta plus pi phi over phi naught plus sine delta theta minus pi phi over phi naught. And now you can use this sine and cosine identity to write this sine a plus b plus sine a minus b as like sine times cosine. Let me just write this. This is 2i critical sine delta theta cosine pi phi over phi naught. And if I look at the current, if you want, I can also take the absolute value here. Or another way of saying this is I critical in the presence of flux goes to this 2i critical times cosine pi phi over phi naught. So this is I critical. Now I want to plot this. So this is something like that. So this one is phi. This one is my absolute value of I critical, which depends on flux. If I have flux 0, I have maximum. Okay. So this is 0. So this is phi naught. This is 2 phi naught. This is minus phi naught. Minus 2 phi naught. And what happens is so it is going to be maximum at 0 and 1, so I need to just do this. Right. Did I get that right? Right? It is, if 0 it is 1, if it is 1 it is also 1, yes. Something like that. Something like that. And this is exactly what we should compare with like double slit experiment, right? In the double slit experiment, we have this double slit and we send in light and we have like a screen, and on the screen we have this so-called Fraunhofer diffraction. And these maximas or minimas are exactly like that. Here, like there are like two paths for the light to go. The light can go like this or it can go like this, and these two paths are going to interfere. And here Cooper pairs can go in the upper branch or the lower branch, and then they interfere, and the path length difference is here is tuned with solenoid flux. By choosing the flux, you can change the path length, and the path length is going to determine the interference pattern. Now, this thing is actually very useful because like this phi naught superconducting quantum flux is 2e over h, right? These are fundamental constants. You can plug in, and what you find is like something like this, 2.07 times 10 to the minus 15 Weber, which is Tesla times meter squared. And now suppose you make, I don't know, 1 centimeter squared. I think they can even make these things like millimeter size, right? What they do is like they have these like nano fabrication, etching, and like some kind of photoresist, whatever they do. They can make them like a sub-micron scale. They can make it very, very small. But suppose we can make this like, I don't know, 1 centimeter squared, which is like what? 10 to the minus 4 meters squared. If you plug in here, the B you can detect from here is like what? 10 to the minus 15 divided by 10 to minus 4, which is 10 to minus 11 Tesla. Right? With this method, you can like detect like extremely tiny magnetic fields. Any questions? Now, like, just to motivate you, these things are really interesting, and they are also very modern, right? These things are developed in like 70s and 60s, but today I think there are a lot of things that they are useful for. But I want to look at it from a fundamental physics point of view. So let's think about. I won't write many equations anymore. Let's think about macroscopic quantum interference and what it actually means, right? So we are saying that there's like interference like light here, but this interference is nothing like we have seen before. So we are talking about like a gigantic collection of electrons in like a big size, like this is like a centimeter size device. I mean, this is almost human scale, right? We can see these things with our eyes, we can look at them, we can hold them. These are not macroscopic physics anymore. And when you carry quantum mechanics to human size, very like strange questions come, right? Like, for example, Schrödinger's example, right? He said that if quantum mechanics were true in the macroscopic size, there's like cats both dead and alive, right? And that doesn't make sense. And his conclusion was, oh, maybe there's like a cutoff at some scale, you stop being quantum and you turned it classical. Otherwise, our world would not make sense. And since we can talk about these devices in human size, we can test these questions in experiments, right? Now, these are not like some philosophical arguments anymore. They are like testable observations. And the first, since I have a little bit of time, let me first ask the question. Can we see any quantum in human scale? Or another way to say this is like, do we have like, right, we are in the like technology age, and do we have any truly quantum machine today? So do we have anything quantum, but computers, anything else? So what in our lives do we have any like use of quantum as in its like truly quantum sense? I mean, like, okay, let me try to explain. First, everything is quantum, right? Because atoms, electrons, they are quantum, but we don't see that, right? There's like quantum in macroscopic scale, but in classical world, for example, like think about metals. Metals are right quantum, right? Electrons, Pauli exclusion, all these things. But at the end of the day, if you do like current versus voltage, if you measure the conductivity or resistance, you have the root result. Right? There are like some quantum parameters, but they don't matter. We observe classical result. Or similarly, think about laser. Everybody says laser is quantum, but right, the way we generate laser is quantum, right? There's like some semiconductor and energy levels, and there's like, I don't know, spontaneous emission or absorption. But at the end, something comes out, and that output is classical, right? The laser, there's like a large number of photons. The parameters of the theory are quantum, but what we observe in a lab is classical Maxwell type of results. Similarly, like semiconductors, electronics, we are saying like, okay, there's like a semiconductor industry and there are like energy bands, but once you determine these parameters, you put it in a classical law, and semiconductors, transistors, they are doing classical currents, and they are classical observations. Even magnets, right? We say magnetism is a quantum, but we can write like a classical equation of motion to describe almost all magnets. So the point is, I think this is a little bit a tricky question, but my answer is no. There's no quantum machine, and there is no truly quantum effect we see in human size today, at least in practical applications. And the question is, how do we quantify something to be quantum or not. Like if I give you an effect, how can you quantify if it is quantum or classical, right? Like quantum effects are quantified with superposition, which is the result, which is the cause of interference. Right? We need to be able to write a state in like a human scale, which is like a superposition, psi 1 plus, I don't know, it could also be minus, doesn't matter, psi 2, like two different states superpose, and that's actually the reason for interference, right? There's like two different states superposed here, upper and lower branch, and because of their superposition, you see the interference. And I want to give you a couple of examples that, I mean, there are no practical applications. We don't have any quantum machine we use today, even including the headlines you may see. I think they are quantum in some sense, but they are at least not doing what we want them to do. But we can see this thing in macroscopic scale. So the answer to Schrödinger's challenge is yes, cat is both alive and dead, and we know it from the experiments. And let me give you, there are actually many experiments, and people do this in like many different unexpected places. But the first one is, so the thing I want to show you is like you have like a macroscopic superposition, and they should also demonstrate this by interference. They need to have an interference effect. One is like Wolfgang Ketterle, 2002. He had like BEC interference, and I think I put the paper, this one. So what he's doing is like, it's not very important. He's creating a macroscopic quantum wave, right? And after he cuts it with a knife, so I don't know, here there's like right side and left side, just like a Josephson junction. And then after separating the cloud, he brings them together, right? Now you have, I don't know, psi left and psi right. And when you bring them together, they interfere. And that's what you see here, like macroscopic interference. And the size of this thing is like, I don't know, it is like probably, he doesn't have it, but these things are typically micron size. I mean, you cannot see it, but if you have like a magnifier, you can see this interference with your eyes. At least these are like camera pictures. So the second one is closer to what we have been talking today, is like so-called Nakamura 1999 so-called Cooper pair box. I think I also opened it somewhere here. So this one. So here what he's doing is like he has like some complicated experimental setup, but in the center of this setup there is like this superconducting island, and inside this superconducting island, well, what we said was the following, right? In a superconducting state we have n electrons, and from these n electrons we can take a Cooper pair or put a Cooper pair, and it is like something like that, psi n plus 2, and I can make a superposition of this. Like unlike here, there is like a different way of looking at the superposition here, and if I can see interference from this state, it is going to prove that it is like a superposition. And what they do is like they look at so-called Rabi oscillations here, right? Let me also try to copy this. And this Rabi oscillation, I don't know if you know it, but if you hear it for the first time, it is kind of like interference, but there's like an oscillation in time, right? Because there are like two states. Think about this like some psi 1, like you can think about a particle in a box. and psi 2. Once you evolve it, it is going to come with e to the minus, okay, this one, minus I over h bar e1 times t, right? And this one is going to evolve with e to the minus I over h bar e2. And if you look at oscillations of anything, for example, density, right? If you look at psi, for example, there is going to be like oscillation in time. And the oscillation is going to be determined by E2 minus E1 over h bar. You can read the paper to see the more detail, but these oscillations are here, right? And with there's some technicalities which is not very important, but I want to highlight the time scale. This is like picosecond, right? Like you are thinking about it, and this is also observation. This is not some simulation. These people can just see at the picosecond scale of these quantum interference effects. And this is also, again, like not some microscopic system like atomic system or electron system. This is a gigantic in the sense of like a microscopic world is like a box with many Cooper pairs. And last one, there are many, but let me also write this one and then finish it there. This one is also quite relevant for today. There are a couple, but let me write this one. So this is Chirescu. This is 2003. And I think what they do is, rather than tuning rather than creating the superposition with the number of Cooper pairs, they are creating the superposition in the phase. And in short, what this is like, if you remember our flux quantization argument, we had something like this. So this was E of flux, this was flux, and if you remember we had something like this. There was like a quadratic potential, and inside quadratic potential we had these minima. And what these guys can do is like, there's like some flux here, let me call this phi 1, another flux minima phi 2. If you want, this is like zero flux, one flux, and they create a superposition like this psi, the superposition of I don't know, psi m and psi m plus 1. Good. Like different flux, and at the end, okay, they are like, again, this is not this one, but this one. The device is a little bit more complicated, but it's not very important. At the end, what you see is like these Rabi oscillations, which is a proof of like macroscopic quantum phenomena. Okay. Okay, I think this is all I wanted to show. If you have no questions, we can stop here, and I'll see you next time.